In today's note, we are going to continue looking at exponents. However, now we're going to look at them in an equation. And we're going to start by looking at exponential growth. So the first little bit is going to look at a little bit of an introduction to kind of the idea of exponential growth. So the first question, we're just kind of going to work with some percents. So the HST is 13% in Ontario. What is the after-tax price of an item that has a sticker price of A, $20 and B, $89.99? So there's a couple ways you could do this. Right? If we have basically the after-tax price is the price of the item plus the tax, or plus 13%. So you could figure out what 13% of 20 is by doing 20 times the decimal value of 13. So 20 times 0.13, and you would get 2.6. So basically the tax on a $20 item is going to be $2.60. So to find the after-tax price, you do 20 plus 2.6, which equals 22.6, or $22.60. That's one way we can do it. However, there is a shorter way that we can do this. Because I am multiplying the $20 times 13%, I want to figure out, is there a way I can multiply it where I'm also including the original value? And the way we can do that is by thinking of the after-tax price is going to be the $20, the after-tax price is going to be 113% of my value. It's going to be 100%, which is the original value or the starting value, and it's going to be 13%, which is the tax added on. So I can take $20 and multiply it by 1.13. The 1 is going to be the original amount. The 0.13 is going to be the tax. And when I solve this, or when I calculate this, I get a value of $22.60. So by having that 1 in the beginning, or that 1 as well as the decimal version of my percent, allows me to just multiply it once, and my final answer will include the original amount plus the 13% that I'm adding on. The same thing can be done in B. The price, or the after-tax price, is going to be $89.99 multiplied by 1, so the original amount, plus 0.13, or the tax, and the after-tax price I get is 101.69. So that's a way where I can multiply by including the original amount plus the tax. For 2, the price of a meal at a restaurant was $42.65. What is the total amount you will pay if you wish to leave a tip of 15% and 18%? So, because we're looking for the total amount, or that means we have to pay the original amount plus 15% of that if we're leaving a tip of 15%. So similar to the last one where I wanted to pay, or the after-tax price was the original amount plus the percentage, it's the same here. So to multiply and get the original amount, I need to multiply by 1, but I'm also adding in 15%, or 0.15. So in other words, I'm doing 42.65 times 1.15, and I get an amount of $49.05. So that means if I wanted to leave a tip of 15%, the total amount would be $49.05. I can do the same thing if I'm dealing with 18%. My total amount is going to be the original, $42.65, multiplied by 1, because again, I have to pay that original amount, plus 0.18, or 18% of that original amount, which would be the tip. So it ends up being 42.65 multiplied by 1.18 and in the end I get $50.33. So it's the same idea. I'm multiplying by 1 to include the original amount, and then I'm multiplying by the decimal version of my percent to include that as well. For number 3, the value of a Mr. Blanchard hockey card is $6 and it grows 20% every year. How much will the card be worth? It should be worth after 1 year. So we know that it's going to be worth still that 6%, or that $6, plus 20%. So to figure out the worth, I'm going to do $6 times 1 for the original amount, plus 0.20 for the 20%. Or basically 6 times 1.2. And in the end, when I multiply that, I get $7.20, or 7.2. So that means after 1 year, the card will be worth $7.20. What do I have to do if I want to figure out how much it'll be worth after 2 years? Well, after 2 years, I can take that original amount, or that amount of 1 year, so 7.2, and I'm going to multiply it by the same thing. Because after 1 year, it's worth $7.20, and then that's going to increase by 20% after the second year. So 1 plus 0.20 again. So for the original plus the 20%, 7.2 times 1.20, and we get 8.64. So that means that after 2 years, the card will be worth 8.64%. Or not 8.64%, $8.64. What we want to do now is complete the table of values and then make a graph showing the value of the card throughout the year. Well, at year 0, the value is 6. So originally it's $6. Next, it's $7.20. After 2 years, it's $8.64. We could figure out what it is again by doing the same thing. So for the third year, we can do $8.64 times 1.2, and I get a value of $10.37. 4 years, again, I take the 10.37 times 1.2, and I get 12.44. 5 years, again, take the same thing, 12.44 times 1.2, and I get 14.93. So that is my values after 5 years, or for every year up to 5 years. Now thinking about it, is there an easier way to go through this and get my other values? Right, rather than find each value and then multiply it by 1.2. Right, if you think about it, every time we're going another year, we're multiplying by 1.2. So 6 years wasn't multiplied by anything. Year 1 was 6 times 1.2. Year 2, it was the previous answer, so 6 times 1.2, also multiplied by 1.2 again. Year 3 was 6.12 times 6 times 1.2 times 1.2 to get the previous year. So this would equal the 8.64. And then we multiply by 1.2 again to get the next year. So it seems that for however many of years we're looking in the future, we multiply 1.12 by that number of years. So 3 years, we have 1.2 multiplied by itself 3 times. 4 years, 1.12 multiplied by itself 4 times. And so on and so on. Right? Very similar to our personal finance when we looked at compound interest. So the next part of the table, and again, we'll come back to that idea. The next part of the table, we're looking at a ratio, and the ratio is kind of like your first differences, but it's basically like your y2 divided by y1. So instead of subtraction, we're dividing. So if I look at my chart, 7.2 divided by 6 equals 1.2. 8.64 divided by 7.2 equals 1.2. 10.37 divided by 8.64 equals 1.2. And you continue that pattern all the way down, 1.2, 1.2. You see that the ratio is all the same. And this ratio is telling us the growth rate. Which is that decimal part, or that 20%. Because the 1, again, represents the original amount. So if we want to go and just graph this to get an idea of what it looks like, we have 0 and 6, 1 and 7.2, 2 and 8.6, 4, 3 and 10.3, 4 and 12.4, and then 5 and 14.9 are basically 15. So if I graph this, I can see that it's not really a straight line. It has an upwards curve to it. So it is a little bit different from linear graphs that I've learned about in grade 9 and 10, and it's also different from the quadratics, right? Because this is not a parabola. I don't see a repetition of numbers. C wants me to come up with an equation relating y, the value of card, to n, the number of years. So I have to think about what math have I been doing. Well, y is going to equal, I know the original value was 6. And to figure out how much it'd be worth after 1 year, I multiplied it by 1 plus 0.20, or that growth rate. And then I did it to the power of n, or the number of years. So if I look back and I see everything in red, for every extra year that I'm looking at, I add on another multiplying by 1.2, which is what an exponent represents. So this is my equation for this relationship. And again, the 20 is the growth rate. So what will the value of the card be after 15 years? Well, I have to plug in 15 for n and solve for y. So 6 plus, we can simplify it to 1.2 to the power of 15. So as long as we're doing our BEDMAS properly, doing the exponent first, so 1.2 to the power of 15, and then multiply by 6, we get our growth rate, our value of $92.44 after 15 years. So let's look at another example. The value of a Mr. Lou hockey card is $4 and grows by 35% every year. So we're going to want to create a table of values and a graph to show this relationship. So at year 0, it's $4. After year 1, it's 4 times 1, because it's the original value. And then we add on the decimal version of our growth rate, so 0.35, and we get a value of $5.40. If I want to find year 2, I do 4 times 1.35 times 1.35 again. The 4 times 1.35 the first time gives me year 1, then I multiply by 1.35 again to get year 2. So which gives me a value of $7.29. If I want to continue this pattern, it's basically 4 times 1.35 to the power of how many years it is. In this case, 3 years. 9.84. Next one would be 4 years, 13.29, and then to the power of 5 for the next one, 17.94. The ratio, so when I divide the bottom by the top, kind of like first differences, except instead of subtraction, we're using division. 5.4 divided by 4 equals 1.35. 7.29 divided by 5.4 equals 1.35. And you kind of see the pattern that we're going to be getting. It's all going to equal 1.35. Because the ratio should tell us the growth rate, which in this case was 35%, or basically that decimal added on to 1. If we want to plot our points, 0 and 4, 1 and 5.4, 2 and 7.29, 3 and 9.8, 4 and 13.2, and 5 and 17.9. So we can hopefully see that this is a steeper curve or compared to the last one, and we're also looking at a higher percent or a higher growth rate. If I want to come up with an equation, again relating y, the value of the card, and n, the number of years, y equals, we know we're starting a value of 4. And if I want to figure out what the value is, I have to multiply it by 1.35. And the number of times I multiply it by 1.35 depends on how many years I'm looking at, or basically to the power of n. So if I want to figure out the value of the card after 18 years, do y equals 4 times 1.35 to the power of 18. And when I enter that on my calculator, I should get $887.29. So after 18 years, the card would be worth $887.29. So everything that we looked at is an example of exponential growth. It's different than linear and quadratic. Exponential growth grows rapidly at a very fast rate. And that rate would be our growth rate. So the general formula for exponential growth is y equals a, which is the original amount or the starting value, times 1 plus r. R is the rate of growth per period, and it's basically the percent as a decimal. So we will see the question tell us a percent, and we have to turn that into a decimal. And then n is the number of periods of growth, so we usually leave that as n, and y is the final amount. So the only two things you actually need to fill in this equation is your a and your r. The y and the n are going to be your variables that represent, or your generalized variables, kind of like your y and your x. But the a and the r you do need to fill in. You need to know your starting amount, and you need to know your growth rate. So for number 5, we need to work on coming up with equations. The population of Whoville is 2,000 people. What will the new population be if Whoville grows at a rate of 5% per year or per month for 6 months? So if I want to come up with this equation, my a value is going to be the starting, which is the 2,000 people, and my r is going to be my growth rate. So in this case, it's 5%, which as a decimal is 0.05. And the 6 months tells me the n value. So y equals 2,000 times 1 plus the rate, or 0.05, all to the power of n, or 6. So when I do that on my calculator, I can simplify at least inside the brackets if you want, 1.05 to the power of 6. And when we calculate that, again, do the exponent first and then multiply, we get a y value of 2,680. So after 6 months at a rate of 5% per month, we get 2,680 as our population. For B, same idea, except now we're given a different growth rate and a different n value. So our A is still 2,000. Our R is now 10%, which as a decimal is 0.10. And our n is going to be 8 years. So in my equation, y equals 2,000 times 1 plus my rate, or 0.10, to the power of n, or 8 years. I can simplify this a bit. 2,000 times 1.1 to the power of 8. And when I simplify this, I should get 4,287 as my new population after 8 years at a growth rate of 10% per year. Looking at a key concept, or just a specific term that we should be looking at, when a population doubles, it is said to grow at a rate of 100%. So if we're talking about doubling something, it's growing by 100%, or is adding on an extra amount of that value. So a picture of Mr. Lou's cat, Chester, costs $4, and it doubles in value every year. Write the equation relating y, the value of the picture, and n, the number of years. So in this case, y equals, the initial value is 4, and it's going to be 1 plus the growth rate. And in this case, because it doubles, the growth rate is 100%. So 100% as a decimal is 1, and to the power of n. And this can simplify to y equals 4 times 2 to the power of n. So this does make sense now that we're doubling. So 4 times 2 to the power of how many years we're going to be looking at. If we want to come up with a table of values, this is going to be a little bit easier because it's easy to do the doubling. So if it starts at 4, after 1 year it doubles to 8 or multiplies by 2. From 8 years, or from a value of 8, next year, if it doubles again, it'd be worth 16, or again multiply by 2. 3 years, 32, 4 years, 64, and then 5 years, 128. And again, we can see, hopefully easier, this equation, because I can do 4 times 2 to get to 8. After 2 years, it's 4 times 2, which is 8, times 2 again. 3 years, 4 times 2, which is 8, times 2, which is 16, times 2, which is 32. Year 4, I can just simplify 4 times 2 to the power of 4, 4 times 2 to the power of 5 for the last year. So hopefully maybe this one's a little bit easier to see that pattern and why we're dealing with kind of this idea of exponents. For the ratio, again, remember we're dividing bottom minus the top. So 8 divided by 4 equals 2. 16 divided by 8 equals 2. 32 divided by 16 equals 2. And we should see that the ratio is the same because it's increasing by that same growth rate. Or 100% every time, or it's doubling every year. If I want to graph this, at 0, it's $4. At 1, it's 8. At 2, it's 16. 3 is 32. 4 is 64. And 5 is 128. So this is an example of exponential growth, and it does look very similar to the compound interest that we looked at in the finance unit. And compound interest actually is just an example of exponential growth. That's why it's beneficial to have compound interest if we're saving money, because it grows rapidly over time. Lastly, C, what will the value of the picture be after 10 years? Well, we could continue this table, or we could use the equation y equals 4 times 2 to the power of n. I now know that n is looking at 10 years, so 4 times 2 to the power of 10, or basically it's doubling or multiplying by 2 10 times. And we simplify this, we get y is equal to $4,096. So after 4 years, or after 10 years, it is $4,096. So again, the main thing, if we go back up, is recognizing what is the equation for exponential growth. Again, the A value is the original amount, the R value is the rate of growth per period as a decimal, and the N is the number of periods of growth, and Y is the final amount of whatever we happen to be looking at, population, dollars, whatever it may be. So again, we should be able to recognize that this is the formula and how to use it or how to determine it, whether we're looking at an equation, or sorry, not an equation, a scenario where we're told the initial value and the growth rate, or if we're looking at a table of values where we can see the initial amount and determine the growth rate by looking at the ratio.